Good morning, everyone. Welcome back to Introduction to Petroleum Engineering. In today's lecture, we will study one of the most important tools in modern reservoir engineering, reservoir simulation. This topic is extremely important because simulation helps us understand how fluids behave in the subsurface, how reservoirs respond to production and injection, and how engineers make development decisions before spending large amounts of money in the field. Before we focus on today's topic, let us place it in the context of the whole course. So far, we have moved from geology and geophysics to drilling, petrophysics, logging, and reservoir engineering fundamentals. Today's lecture is part of the development stage, where we move from understanding rocks and fluids toward predicting reservoir behavior. This slide also reminds us of the difference between reservoir modeling and reservoir simulation. Reservoir modeling is mainly the construction of a static 3D representation of the subsurface. It tells us where the structures are, how the rock properties vary, and how the reservoir is organized spatially. Reservoir simulation, on the other hand, adds time. It uses the static model to predict how oil, gas, and water move, how pressure changes, and how the field may perform under different development strategies. So, in a very simple way, you can think of reservoir modeling as building the reservoir picture, and reservoir simulation as making that picture come alive over time. Today's lecture has 4 major parts. First, we begin with an introduction to reservoir simulation. Second, we discuss the theory behind it, especially the conservation laws and the mathematical ideas that support simulation. Third, we look at the typical workflow and tasks involved in building a simulation model. Finally, we conclude with key learning points and what comes next. I want you to follow these 4 parts carefully, because by the end of the lecture you should not only know what reservoir simulation is, but also why it matters and how it is actually used in petroleum engineering. Reservoir simulation is a tool developed by combining physics, mathematics, reservoir engineering, and computer programming in order to predict hydrocarbon reservoir performance under different operating strategies. This is a very powerful statement, because it shows that simulation is not just software. It is the integration of scientific principles, engineering judgment, and computational methods. The main purpose of reservoir simulation is to gain insight into reservoir recovery processes. For example, if we change production rate, if we inject water, if we inject gas, or if we shut in a well, the simulator helps us estimate how the reservoir may respond. On the figure, you can see a kind of loop. Data and assumptions go into the model. The computer program processes them through mathematical equations, and then we obtain outputs such as pressure forecasts, recovery estimates, and fluid distributions. So a reservoir simulator acts like a virtual laboratory for subsurface systems. Instead of testing expensive ideas directly in the field, engineers can test them first in the model. At the same time, we must remember that reservoir simulation is not magic. It leads to predictions of reservoir behavior, but it is always influenced by the assumptions we make, the simulator we choose, and the quality of the model setup. Simulation studies can be subjective, and different simulators may produce somewhat different answers because of differences in numerical schemes, physics options, or user choices. This means reservoir simulation is not about getting one perfect answer. It is about constructing the best possible representation of reservoir behavior using the information available. So whenever you see simulation results, you should ask, what assumptions were used, what data supported the model, and what uncertainties remain? This slide gives one of the most important warnings in all of simulation. A computer program based on a mathematical model needs reliable input. No simulator can replace reliable data or the brain of the user. In other words, if poor data goes into the model, poor results will come out. This is the famous GIGO principle, garbage in, garbage out. Why is this so important? Because students sometimes think that more advanced software automatically means more accurate results. That is not true. If porosity is wrong, permeability is wrong, fluid properties are wrong, or well controls are unrealistic, then the forecast will also be wrong. The user's role is absolutely essential. The engineer must validate the data, understand the geology, choose sensible assumptions, and interpret the results critically. The simulator is a tool. It does not think by itself. Let us briefly look at the history of reservoir simulation. From 1950 to 1970, simulation focused on 2- and 3-dimensional models with simple geometries, black oil fluids, well coning, and multiple wells. From 1970 to 1980, more advanced compositional, thermal, and miscible models were introduced. From 1980 to 1990, the industry addressed more complex well management, fractured reservoirs, and fault gridding, and graphical interfaces improved usability. In the 1990s, we saw stronger integration with geomodeling, geomechanics, parallel computing, and local grid refinement. Then in the 2000s and beyond, machine learning and deep learning began entering the field. This timeline is useful because it shows how reservoir simulation evolves with engineering needs and computational power. As reservoirs became more complex and development strategies more demanding, simulation methods also became more advanced. Why do we build reservoir models in the first place? There are several key purposes. We use models to estimate field performance, plan development, visualize the reservoir, calculate volumes, and support well planning. Let me explain each one briefly. Estimating field performance means forecasting production, pressure decline, water breakthrough, and recovery. Development planning means deciding how many wells to drill, where to drill them, and how to manage injection and production. Visualization helps engineers understand a complicated 3D subsurface system. Volumetric calculations help estimate hydrocarbons in place. And well planning uses the model to guide drilling targets and operational strategy. So the reservoir model is not just an academic exercise. It is a decision support tool. This slide includes an important idea from Underhill. In reservoir simulation, the question is not whether to model, but how and how much. In other words, the degree of model sophistication should depend on the complexity of the engineering question and the amount and reliability of available data. If the question is simple and the system is simple, then a simple model may be enough. But if the reservoir is highly heterogeneous, the fluids are complex, and the development mechanism is complicated, then a more sophisticated model becomes necessary. A good engineer does not always build the most complex model possible. A good engineer builds the most appropriate model for the problem. Here we see the relationship between heterogeneity, fluid type, and development mechanism. The key message is that not every reservoir requires the same modeling effort. If the reservoir has low heterogeneity, simple fluid behavior, and simple depletion, sometimes analytical methods may be enough. But when heterogeneity increases, when fluids move from dry gas to heavy oil, or when development moves from natural depletion to water or gas or steam injection, simulation becomes much more necessary. So this slide teaches an important engineering judgment. We build models when reservoir complexity justifies them. Heavy oil reservoirs, reservoirs with strong aquifer support, gas injection projects, and steam processes are all examples where simulation is often essential. This slide summarizes three major elements of reservoir simulation. The first is geological description. The second is fluid type. The third is reservoir depletion mechanism. For geological description, we need to know the framework of the reservoir: structure, layering, faults, porosity, permeability, and heterogeneity. This may be treated in a deterministic way, where values are fixed, or probabilistically, where uncertainties are represented through multiple possible scenarios. For fluid type, the choice between a black oil model and a compositional model is critical. Black oil is usually sufficient for many conventional oil reservoirs. Compositional models are needed when detailed phase behavior matters, such as gas condensate systems, miscible gas injection, or CO2 storage. For depletion mechanism, we must understand whether production is driven by natural depletion, water influx, water injection, gas injection, or thermal methods. All of these affect the simulation strategy. This slide contrasts deterministic and probabilistic thinking. A deterministic process has no randomness in its outcome once the inputs are fixed. For example, converting feet to meters is deterministic. The output is fully defined. A probabilistic process includes chance. You may know the probability of an event, but not exactly when it will happen. The example here is rolling a die until a 3 appears. Why does this matter for reservoir engineering? Because some parts of reservoir modeling are deterministic, such as solving equations after we define inputs. But many parts of the subsurface problem are probabilistic because the real reservoir is not fully known. So uncertainty is naturally embedded in reservoir work. In reality, reservoir models combine both deterministic and probabilistic components. Deterministic modeling gives us a structured framework based on known geology, such as stratigraphic surfaces or depositional interpretation. Stochastic or probabilistic modeling helps represent uncertain spatial properties such as porosity and permeability distributions. This combination is extremely important. If we use only deterministic thinking, we may ignore uncertainty. If we use only stochastic thinking, we may lose geological realism. Good reservoir modeling integrates both. Geological interpretation provides the framework, while geostatistics helps us explore the range of plausible property distributions. That is why reservoir engineering is not just number crunching. It is also about integrating data and uncertainty thoughtfully. Once static modeling is completed, the next step is to build a dynamic model and validate it using production data and well tests. This dynamic model is what we usually call reservoir simulation. Its purpose is to forecast future performance and support field development planning. This is a very important transition. The static model tells us what the reservoir looks like. The dynamic model tells us how it behaves. In practice, the quality of the dynamic model depends heavily on the quality of the static model that feeds it. The aim of gridding in reservoir simulation is to convert the geological model into a discrete system in which the flow equations can be solved numerically. Two common coordinate systems are shown here: Cartesian and cylindrical grids. Why do we need grids? Because the real reservoir is continuous, but computers solve equations on discrete elements. So we break the reservoir into cells or blocks. Cartesian grids are simple and common for many field-scale problems. Cylindrical grids are useful near wells or around radial flow patterns. the choice of grid affects both accuracy and efficiency. A finer grid captures more detail but requires more computation. A coarser grid runs faster but may miss important features. So grid design is one of the first major engineering decisions in simulation. Here we move from general gridding to discretization in space and time. Spatial discretization means dividing the geological model into blocks along x, y, and z directions, so we can solve the governing equations from block to block. Temporal discretization means dividing the simulation period into time steps, delta t, so we can follow changes over time. These two concepts are fundamental. The reservoir is not only distributed in space, but also evolves over time. Pressure changes, saturations change, and production changes. Therefore, the simulator must track both spatial differences and temporal evolution. A smaller block size and a smaller time step can give more detail, but they also increase computation time. Again, reservoir simulation is always a balance between realism and practicality. This slide highlights two related issues in grid selection. First, how accurately does the grid match the geological description of the reservoir? Second, how well does the grid support numerical discretization of the flow equations? A simple coarse regular grid may be computationally efficient, but it can miss important geological features such as faults or complex layer geometry. A geology adaptive grid aligns better with bedding planes and structural features, which improves realism, but also increases computational cost. So there is no universal best grid. The best grid is the one that is sufficiently accurate for the engineering purpose while remaining computationally manageable.